Hello everyone, welcome back to the channel. So today's video is on the interconversion of structural representations in organic chemistry. So in organic chemistry, there are different ways in which we can represent a molecule or a compound. Like if I have a compound, it would have its molecular formula, then it would have a condensed structure, then I can write a complete structure where all the bonds are shown separately, or a simple bond line structure where just straight lines are used to represent the structure, or it can be in a wedge form where I have wedges which represent whether my groups are present in the plane, out of the plane, or it is present into the plane. Then I can have a Fisher projection, and then we have the Sawhorse projection and Newman projection. The Sawhorse projection, Newman projection can exist in two different conformers, that is the eclipse conformer form and the staggered form. Conformer means how we arrange the spatial arrangement of atoms or groups in space that give rise to the conformers, eclipsed form and the staggered form. Right. These are the different ways in which we can represent a molecule. Here I have taken the example of butane. The simple butane molecule can be represented in all these different ways. Now in organic chemistry, or especially in stereochemistry, specifically, we can convert from one form to the other. That is the last row. That's Wedge, Fisher, Sawhorse and Newman. It's possible to interconvert from Wedge to Fisher, Fisher to Wedge, Sawhorse to Newman, Newman to Sawhorse, Fisher to Sawhorse, Sawhorse to Fisher, Fisher to Newman, Newman to Fisher. So totally 8 conversions are possible. So in this video, we'll be looking at one by one. We'll be looking at the how we can convert each of them to another form. Let's start with the first conversion, which is wedge to Fisher form. So before we move into the conversion part of it, let us see what each bonds represent in a wedge form and in the Fisher form. So here we have the picture or the image of a molecule in its wedge form. Now, what are these different bonds representing? I have the straight line bonds. Then I have this wedge bond, solid wedge bonds. Then I also have this dashed line bonds. So what do each of them represent? So the lines, the solid lines that I have connecting my central carbon atom, the chiral carbon atom and the CH3 group and the hydrogen group. Those solid straight lines, they represent the groups that are lying in one plane. Understood. Now I have this dashed line which represent OH group is attached to the chiral carbon atom via dashes, and that represents that my OH molecule is pointed into the plane. Like if I have a paper as my plane, like CH3 and H would be in the plane and my OH would be projecting towards me, like into the plane, and the Br, which is represented by the wedge, would be presenting away from me. It's moving out of the paper. Understood. This is what each of these bonds represent. Now we have to convert it to the Fisher form. Fisher form means it would be like in the form of crosses. I would have lines in the form of crosses where I have the slanting line and the sloping line. So what are these lines? The vertical lines are there and the horizontal lines are there. Now which all molecules should I place on the vertical line and which all molecules should I place on the horizontal lines? We'll look into it. And the point where the cross meets, this particular point that I have here is my chiral carbon atom. So I have my chiral center there and I have to mark all the 4 different groups around it along the vertical line and the horizontal line. Okay. So to convert from the wedge form to the Fisher form, along the vertical line of the Fisher, the straight line, the standing line, so along the vertical line, I have to represent those groups which are present in the plane of the molecule. That is, which all molecules are in the plane? This CH3 and this carbon and this hydrogen. These are the 3 groups. So I can represent them along the vertical line like CH3. Then I have this chiral carbon atom here and I have my hydrogen group here. Right, this is how I have the groups. Now, which groups go to the left in the horizontal line and which groups move to the right of the horizontal line? In the wedge projection, whichever group is represented by the dashed line, that would retain its position, which means that if my dashed line is on the left side, dashed lined group is on the left side, then it means that even in the Fisher projection, it would take up the left position. And if my dashed lines are on the right side, are given in the right side, it would mean that in the Fisher projection also, my dashed line group would take up the right side. So whichever position it is sitting in the wedge form, the same position would be taken up in the Fisher form also. And the solid wedges, they would revert its position. If it's in the left side in the wedge form, it would take up the right side position in the Fisher form. Understood? So now I can say that here my OH group is represented by the dotted line dash lines, and it is on the left side in my wedge projection. So it has to retain its position, and in the Fisher projection also it would take up this left side here. So my OH would be on the left side, and my BR, which was actually on the left side, represented by solid line in the wedge form, but when it comes to the Fisher form, it would change its position to the right side. So this is how I can convert from wedge form to Fisher form. Okay. Now let's take this example where I have two chiral carbon atoms. Earlier I had only one chiral carbon atom. Now I'm having two chiral carbon atoms. So now here we can see that what all are the molecules. This is like 1, then 2, then third carbon and the fourth group. So these are all lying in one plane. These straight lines represent those groups which are in the plane. So these are all lying in one plane and they have to be along the vertical line. Okay. So let me, in the Fisher projection, one CH3 would be here. Here I have my C2, then I have my C3, and that last fourth group CH3 is here. Now, in the carbon 2, so considering this the carbon mark 2, C2, I have my OH and Br on the left side. So the lines, the dashed lines represent OH group, and dashed lines should retain their position. So in the wedge form, the OH group having the dashed line is on the left side. So in the Fisher projection also, my OH group would be on the left side, whereas my Br group would change its position because it is represented by solid wedges. Now coming to the third carbon, my NH2 and COOH groups are on the right side. And so my dashed line group should retain its position, which means that what is represented by my dashed line? NH2 is represented by my dashed line, and NH2 represented by the dashed line is on the right side in the wedge diagram. So that dashed line group would retain its position, which means that my NH2, even in the Fisher projection, it would remain on the right side. So my NH2 would be here, but my COOH has to interchange its position because it is represented by solid line. It was in the right side, now it will change to the left side. So my COOH group would come here. Understood? Now let's look at the reverse process, that is from Fisher to wedge. So I have a Fisher structure here and I can convert it to the wedge form in two different ways. So two arrangements are possible. One is the case where I have my wedges and my dashed lines on the right hand side, and the other case is where I have my dashes and the wedges on the left hand side. So let's see how we can convert the groups in each case. So in the first case, those straight lines in the wedge form, they represent the groups in plane. And what are the groups in plane? They are the ones that lie on the vertical line in the Fisher projection. Which groups are lying on the vertical line in Fisher projection? CH3, central carbon, and the OH groups. So I should represent them on the straight lines in the wedge form. That is, here I can represent my CH3, then I have my central carbon and have my OH group. This is what I have, right? Now, coming to the wedges and the dashes. So my wedges and dashes are lying on the right hand side, and the dashed line group should retain its position. So whatever is represented by the dashed line in the wedge position on the right hand side by the dashed line in the wedge form, the same group would be present on the right hand side of the Fisher form also. So which is on the right hand side of the Fisher? BR. Since BR is on the right hand side of in the Fisher projection, the same BR would be on the right hand side represented by the dashed line. So my BR would take up this dashed line position and hydrogen would take up the wedge position. Understood. Now coming to the second case where my dashes and wedges are on the left hand side. So again, the groups in the plane, that is my CH3, central chiral carbon, and the OH group, they are lying in the plane. First, I should represent them by the straight lines. So I have my CH3, I have my central carbon, I have my OH group. Understood. Now the groups on the horizontal line, those are the ones which are lying out of the plane and into the plane. Now which would be represented by the dotted line and which would be represented by the straight line. So since these two groups are on the left hand side in the wedge projection, so the group on the left in the Fisher projection would take up the dotted line or the dashed line. So which group is on the left side in the Fisher projection? H. So since H is on the left side in the Fisher projection, that same hydrogen group would take up the dotted line or the dashed line in the wedge projection when it is on the left hand side. Right here. So this hydrogen would take up this position and Br would take up the other position. So this is how we can convert either from wedge to Fisher or Fisher to wedge. The only thing is that my groups that are in plane would be along the vertical line, and the groups that are out of plane and into plane would be along the horizontal line, and the vertical line group, no, and the dotted line, dashed line groups would retain its position. If the dashed lines are on the left hand side in the wedge projection, so even in the Fisher projection, that group would take up the left hand side and the other solid line, a solid wedge group would revert its position. Understood. Next is the conversion from Fisher to Sawhorse. So in Sawhorse, how do we have the groups? This is how we have the groups in Sawhorse. Now in Fisher to conversion to Sawhorse form, so direct conversion from Fisher to Sawhorse would give the eclipsed form. Okay, it won't give the staggered form, it would give the eclipsed form. When I convert directly from Fisher to Sawhorse, I'm getting the eclipsed form, and those on the vertical lines are the ones in the plane. That is, I have my CH3, I have my carbon atom, first chiral carbon atom, then I have my second chiral carbon atom and the OH group. These are on the vertical line, and those should be the ones that is represented by which all places. This is like 1, 2, 3, 4. So these sides would be represented by which all groups? 1, 2, 3, 4. Starting from bottom to top, this is how I should be representing. So at position 1, it means that at position 1, I will have my OH. Then position 2 is my carbon. Position 3 is again a chiral carbon. And position 4 is my CH3 group. This is how I should represent. Now along both sides, I'm having two legs. Left hand side I'm having leg and the right hand side I'm having legs. So in the Fisher projection, the groups that are on the left would be on the left leg of the Sawhorse form, and the groups that are on the right hand side in the Fisher projection, that would take up the right legs in the Sawhorse form. So around the carbon 2, I have my Br group on the left side. So here also my Br would take up the left leg, and in the Fisher projection, at the second carbon atom, chiral carbon atom C2, I'm having my hydrogen on the right hand side. So that would take up the right leg. Now coming to the third carbon, so whichever is on the left will take up the left position, and whichever is on the right will take up the right position. Hydrogen is on the left side, so even in C3, my hydrogen would be on the left side and Br is on the right side. So here in the Sawhorse form also, Br would take up the right hand side. This is how I can represent. So I get it in the eclipsed form, that is starting from the bottom to the top, the vertical lines are represented first. Then the ones on the left would go to the left side in the Sawhorse form, and the ones on the right would go to the right legs on the Sawhorse form. It's very simple. Now let's go for the reverse conversion, that is from Sawhorse to Fisher. So the condition when we convert from Sawhorse to Fisher is that my Sawhorse molecule or Sawhorse conformation should be the eclipse conformation. Then only I can convert it to the Fisher form. But in this case, I'm having my Sawhorse in the staggered form. So the first step is converting the staggered form to the eclipsed form. How do I convert the staggered form to the eclipsed form? By rotation. That is, I keep one of the carbon atoms fixed, and the other carbon atom, above the other carbon atom, I rotate the groups by some angle, 60 degree, 120 degree. I can rotate about one of the carbon atoms to make a conversion of Sawhorse from eclipse to staggered, from staggered to eclipse form. So let's do that first. So the first front carbon atom that I have carbon here, I have a CH3 group, I have OH, and I have my NH2 group. Let me keep it as such. Let us not touch that. But the other carbon atom that I have, the second carbon atom that I have, the whole angle, this much angle is 120 degree. But if I take the half of it, means it would become 60 degree. Half of it would be 60 degree. So if I rotate about that carbon atom by 60 degree, then I would get the structure in the form of a eclipsed structure. So when I rotate about this carbon atom by 60 degree, the COOH group would come here, my Br group would come here, and my pH group would come here. Now did I get it in the eclipsed form? Yes, I got it in the eclipsed form. Now let's convert it to the Fisher form. So Fisher form means the second carbon atom, I have to start from the bottom. The front one corresponds to the bottom carbon. The front carbon in the Sawhorse form corresponds to the bottom carbon in the Fisher form. So CH3 starting from the bottom. Carbon, then this carbon, and this COOH. Yes. Now the legs, left hand side legs and the right hand side legs. Left hand side leg, whatever group is there, that would correspond to the left hand side group. So here in this case, my OH would come here and the pH would be here. Now coming to this side, it's the NH2 group which is on the right hand side for this carbon, and it is the Br group which is on the right hand side for this carbon. So this is how I would get my Fisher form for this Sawhorse structure. Understood? Now let's convert from Fisher to Newman. So when I convert from Fisher to Newman, I get similar to the Sawhorse conversion. Newman structure also, I get it in the eclipse conformer rather than the staggered. I wouldn't get the staggered form, I get the eclipse form. Now, how do I convert it? I have two chiral carbon atoms here, as you can see. One carbon, this is C1, and I have a C2 here. So similar to that, in the Newman form, this is my C1, and the behind that, represented by the circle, I'm having my C2, the behind carbon. So whichever groups are on the left side in the Fisher projection would be represented by the left leg here, and whichever groups are on the right side would be represented by the right leg here. So when I consider the carbon 1, C1, bromine is on the left hand side. So even in this form, my bromine should be on the left hand side and hydrogen is on the right hand side to this. So here also my hydrogen should be on the right hand side. So obviously my third group OH would go on top. OH would be here. Now coming to the next carbon, the second carbon, hydrogen C2, hydrogen is on the left hand side. So my hydrogen I place here. Bromine is on the right hand side in the Fisher projection. So I place my bromine here, and obviously my last group CH3 would go on top. So CH3 would come here. It's very simple. Whichever group is on the left in the Fisher projection would take up the left leg here, and whichever group is on the right position would take up the right leg here. And the third group would obviously be on the top. This is how I get it in an eclipsed form. Understood? So now this one is to be converted from Newman form to the Fisher form. But we know that we can't directly convert a staggered form to the Fisher form. So it should be first made into the eclipse form. So that's the first process. I have to convert this Newman structure from staggered to eclipse form and then convert it to the Fisher form. Now how do I convert the staggered to the eclipse? By rotation. Keep one of the carbon atoms fixed, and around the second carbon atom I can rotate the groups by 60 degrees to get the eclipse form. Okay. Now I have two carbon atoms here, like I have my carbon 1 and I have my C2 carbon 2 here. So around the carbon 1, let me keep the groups fixed, like this pH, this Br and this CH3 is fixed. Okay. The other groups that I have, this OH, I can rotate by 60 degree. Then this hydrogen that I have, I can rotate by 60 degree. And this fluorine that I have, I can rotate by 60 degree so that they come in the eclipse form. So when I rotate this OH, by 60 degree, OH comes behind the pH, hydrogen would come exactly behind the CH3, and this fluorine also would come exactly behind the bromine. Now, second case is, now I have to convert that to the Fisher form. So I have my C1 here, I have my C2 here. So in C1, so which was my C1? This was my C1. So in the C1 form, of the eclipsed form, what is on the left hand side? Bromine is on the left hand side, Br. So even in the Fisher form, when I write, my bromine should be on the left hand side. So bromine comes here on the left hand side. Now what was on the right hand side? CH3 group. So even here my CH3 group would come on the right hand side. And what was on the top? pH. So the remaining pH would be the third group that comes here. Now coming to C2. What is on the left hand side of C2? Fluorine. Fluorine is on the left hand side of C2. So I write that here. And what is on the right hand side group attached to C2? Hydrogen. So I write that hydrogen on the right hand side and the remaining OH would come here on top. This is how I can convert from Newman to Fisher. Here, the next conversion is from Sawhorse to Newman. So when I convert from Sawhorse to Newman, if I'm having an eclipsed Sawhorse form, that would give an eclipsed Newman form. And if I have a staggered Sawhorse form, that would give a staggered Newman form. So I don't have to convert anything. So in whichever conformer my one structure is, the same conformer it would give in the other form also. Okay. So here it's very simple. It's like one of it is lying in this top direction, one of it is lying in the bottom direction, and they would just come together closely. They would just come together. So that's only thing here, nothing complicated. So here I have my carbon 1, here I have my carbon 2. So in this Newman form, this would be my carbon 2, and behind I would have my C2. This is C1, and then I have my C2. So in the Sawhorse form, the groups on the left would be the same. The same groups would be on the left side in the Newman form also. So around C1, my OH is on the left hand side here. So that OH I place there. And my NH2 is on the right hand side in the Sawhorse form. The same NH2 I place on the right hand side in the Newman form. And CH3 is on top. I place it as such. Coming to the next C2, COOH group is on the left hand side and Br group is on the right hand side, and my pH group is on the bottom. So this is how I would get. I just have to write the groups as such. Those on the left would go to left, those on the right would go to right, those on top would be top, and those on the bottom would take up the bottom position. It's very simple. Now let's look at the last conversion, that is from Newman to Sawhorse, the reverse. Again, eclipsed Newman conformer would give the eclipsed form of Sawhorse, and the staggered Newman conformation would give the staggered form. Like the case of Fisher, I don't have to do any conversions. So it's very simple. So here, since my Newman form is in the eclipsed conformer, I would get my Sawhorse also in the eclipsed conformer. So this is my C1 and behind I have my C2. So similarly here, this is my C1 and behind I have my C2. So which is on top for C1? CH3. Which is on left? OH. And which is on the right? NH2. So I write all that. Coming to C2, which is on the left? Br. Which is on the right? NH hydrogen group. And which is on the top? It is the pH group. So just look at this structure, and whichever is on top, that would take up top position here also. Whichever is on left, that would take up left position here also. Whichever is on right would take up right position in Sawhorse form also. That's it. Understood. So all these conversions are very simple and easy ones, and you can try out more examples. So that's it for today. Thank you so much.